Yes, I start because it's already 12 o'clock, whoever is come in. So today's lecture is actually a very simple lecture and it's not a lot of statistics. So why I decided to do this lecture, it's because when I received data requests from researchers, there's a bit of misunderstanding about difference, what proportion, what prevalence. So they asked me to do analysis on something when actually you cannot do analysis of prevalence because whatever they want to compare, it's actually not prevalence and stuff like this. Also, when we're doing different models, we present our results in different ways. Like sometimes we present hazard ratio, sometimes we present relative risk, and sometimes odds ratios. And there is rationale between the modeling and what present and why. So I think it will be important to understand the differences. So today's lecture is navigating the data jungle, demystifying proportion, rates, ratios, and relative risk. So the objective of this lecture will be differentiate between all those and understand the significance in different contexts. Also, I will talk a little bit more during this lecture about relative risk, because like later next year, we have some sessions about modeling and like I will talk more about odds ratios and hazard ratios then, but there is a bit less models that actually you present the results as relative risk. So I will talk about relative risk with a bit more. And I will try to show some examples from the literature or my own examples of how it should be calculated. Also, this lecture in the beginning will be pure mathematics because I want every one of you to understand some very simple mathematical concepts. So we know when we read different papers and different articles in the journals, especially in epidemiology, people that don't work a lot with statistical epidemiology, they may get confused between different terms. And I actually learned it my way that even in the printed literature, sometimes the simple words like proportion, prevalence got misrepresented. And sometimes if you don't know those basics concept of statistics, it's really hard to understand the epidemiological papers that we want to use. So the first concept, very simple, it's ratios and proportion. So what is ratio in mathematics? Ratios in mathematics is express the relationship between two quantities, A and B. And usually we say ratio A to B. And in this case, A and B usually non-zero numbers. We're not comparing zeros. And we say A to B in order to distinguish between ratios and simple fractions. For example, if in our box there is one blue rectangle, for every 3 red rectangles, the ratio of red to blue will be 3 to 1, or blue to red will be 1 to 3. For example, we can say today in our medical office we see 3 older patients and only 1 young patient. So the ratio between older and younger patient in this case will be 3 to 1. So when we have the ratio, we very often want to simplify ratios. So, and we need to simplify them in the correct way. So usually we simplify them to smallest whole number. So we find the basically greatest common factor between them and divide them accordingly. So for example, if I can say, oh, today in my office, I had 21 older and 7 younger patients. So the ratio between older and younger patients will be 21 to 7, or basically 3 to 1. What are proportion in mathematics? And I want to distinguish between proportions. We use comparison of proportions in statistics and the meaning of proportion in mathematics. In mathematics, actually proportion, it states that 2 ratios are equal. So mathematical proportion states if 2 ratios are equal. And here you can have some pictures when you see what we say, sometimes say, is it proportional or proportionally? So you can see from the pictures below that the way the photographs were made, it's not necessarily proportional because the things you see in perspective are not equal. So for example, in this case, the example I gave in the previous slide says that 1 to 3 and 7 to 21 are proportional. It means they're equal. So another important understanding of ratios and how ratios are different from percentages and how we can transfer from ratio to percentage. So when we calculate, when we're talking about ratio, we actually calculating part-to-part comparison, younger people to older people that come to our office. When we're talking about percentages, we comparing part to all. So basically, if we had 7 younger patients in our office and 21 older, so altogether 28 patients visited us during this day, so we can calculate proportions of younger and older people that that came to our office during the day. So to summarize, a proportion is part, share, or number of considered in comparative relationship to wall. The smallest value for proportion is 0 and the largest is 1. Yeah, so proportion can be between 0 to 1. If you want to like it, and if you want to translate them to percentages, we multiply by 100. So here we're talking about proportion and statistic. How many male and female are in the population? What is the age distribution in our population, and everything else we presenting as proportions. So usually, for example, for your papers, when you do basic characteristic description, either for your sample or for comparison between your main exposure group, you usually present count and percentage. It's actually proportion out of total population. And usually in those tables, when you have exposed and not exposed people, like in your table, you also will present the statistical values as p-value to evaluate if there is difference between proportions. Prevalence. Now, there is always confusion between prevalence and proportion, because prevalence, it is proportion, but it's very specific proportion. Prevalence actually is proportion of the population who have specific characteristic in given time period. So yes, it's proportion, but it's proportion that calculated specific way. For example, prevalence of HIV in Vancouver in '96. Yeah, or prevalence of HCV in BC population during last 10 years. So we can calculate proportion of specific condition and during the different period of time. We just need to specify for what point we present in our prevalence. So basically, how you calculate prevalence in this case, prevalence is the number of people in the sample with characteristic of interest divided by total number of the people in the sample. So we can, same as proportion, we can present prevalence as percentage or as the number of cases by 10,000 to 100,000 population and so on. And there are several ways to measure and report prevalence depending on time frame or estimates. For example, if you received your prevalence of 0.00003, you might want to present it not like this as per 100,000 population, something like this. You can decide which base you would like to use, so the data you present will look reasonable in your table. How prevalence is reported? Usually there is 3 definitions of prevalence. There is point prevalence, period prevalence, and lifetime prevalence. And on the picture before, you actually see how it's calculated. Point prevalence is you calculating something in specific point. What is prevalence of HIV today in our population? You're only calculating it at one point. Period prevalence is prevalence calculated during specific time point. What if prevalence of specific health condition within past 12 months? And lifetime prevalence, it's proportion of the population that at some point had a specific characteristic. So for example, if you're looking for population of BC of people from birth to death, and we're estimating what was prevalent of HIV during like lifetime. So now when we talked about the prevalence, I want to talk about relative risk. Why I'm talking about relative risk right now? Because relative risk is actually a ratio. And what is relative risk ratio? It's the risk of events for the exposed group and divided by risk of the events of not exposed group. For example, on the picture you see after in your population, 4 people were exposed to drugs we are testing and 8 people were not exposed to the drug, and we can measure condition in both of those populations. Those relative risks provide an increase or decrease in the likelihood of the event based on some exposure. Yes, so it's likelihood of something happening based on exposure. So we need to have exposed and not exposed people in our population. Relative risk has a benefit of being a ratio of risk, which means it can be applied to population with different disease prevalence. Yeah, so exposed and not exposed people might have different prevalence, but we can report our results at the risk as the risk between exposed and not exposed again. Relative risk does not specify the absolute risk of the event, but by rather higher or lower likelihood of the event in the exposed versus not exposed population. So if I think that smokers have 25% more risk to die from specific type of cancer, I'm reporting the relative risk. From this relative risk, you will not be able to know what is risk of non-exposed people that don't smoke and risk of people that smoke. So you need to distinguish for absolute risk. Absolute risk will be calculated for each specific population in your analysis, and relative risk will be the ratio between them. So example of relative risk. So I show how it's calculated and how it's presented. Assuming relative risk of developing lung cancer event, it will be our event or outcome will be developing lung cancer in smokers that are exposed group versus non-smokers that will be our non-exposed group. What the probability of developing lung cancer for smoker, so relative risk will be developing of lung cancer for smokers divided by probability of developing lung cancer for non-smokers. So in this case, we need to calculate the probability of the event and divide two probabilities to get the relative risk. So assuming we hypothetically found that 24% of smokers and 2% of not smokers develop lung cancer, because if you saw the picture in my previous slide, in addition to smoking, there is additional risk factors to lung cancer that we're not including in the specific calculation right now, because we're not doing any modeling, we're just calculating simple relative risk for specific exposure. So absolute risk for developing cancer for in the, oh, I made a mistake, it's non-smokers, should be non-smokers. So a absolute risk in developing lung cancer in smokers population is 24, and risk in non-smoker population is 2. So I divide 24 by 12, and my relative risk will be 12. What it means that the smokers are 12 times more likely to develop lung cancer condition than non-smokers. So I will give additional example of calculation of relative risk, assuming we have study of new medication and we would like to measure specific side effects. So we give whatever medication, some random medication, to our group of volunteers. They wanted to participate in our clinical studies. And 14 volunteers who given new medication had upset to stomach after that, and 42 didn't. So, and volunteers who didn't take the medication, so the risk was really low. Only 2 people develop upset stomach and 83 not. So again, 14 volunteers from those that administered the medication, 14 had the condition and 42 no, and for those didn't, 2 and 83. Now we're going to calculate the probability of having upset stomach with exposure to new medication. So it will be 14 divided 14 for 42, it will be 0.25. The same way we're going to calculate the probability or risk of having upset stomach in non-exposed groups. So it will be 2 divided by 85, it will be much lower, 0.024. And now we can calculate the relative risk of having side effect of upset stomach in our clinical trials of new medication. So basically, in this case, volunteers exposed to new medication are 10.54 times more likely to have upset stomachs than those that didn't take a new medication. And based on this one and additional measures, we can decide if our new medication is working, and if the percentage or risk of having an upset stomach is really high. So I want to talk about relative risk and its clinical significance. And this is very known case in like epidemiology, and you can find a lot of papers about it. Basically, in October 95, UK Committee on Safety on Medication advised that combined oral contraceptive that contains some new hormones were associated with twice the risk of venous thrombosis compared with older products. So basically, there was some older contraceptive. They compared between older and new contraceptive, and they decided that the risk of having thrombosis will be twice more. So actually, the paper, when I took this example form, that said that this advice will be done basically on that 3 studies that were not published. And they say also in those studies, the confidence intervals were not given estimates. So they decided to do this announcement based on something that they think is important. So what happened after that? A lot of people stopped taking the pills, and the rate of abortion significantly increased in UK. Because it's also not only making a statement of risk, it also was how the data was presented. Because they said, oh, we will have a risk as twice high. But actually, what they were supposed to tell is that women in this case perceiving a doubling risk to be too high, and they decided not to take the medication. But actually, if we calculate the relative risk correctly and based on correct data, we can show that results are, that the risk is not as high as we assumed. For example, the risk of developing blood clots without taking a contraceptive was 1 for 700 women. But when they measured the same risk in a woman taking contraceptive, yes, the effect was doubling, but it wasn't twice more. It was 2 women for 700 population. So basically, if we calculate the relative risk of this one, so having blood clots or venous thrombosis after taking new medication was actually not doubled. It increased, but not by much. So it's why I'm giving this example, because it's very important to understand what you're presenting, how you're presenting, and how you calculated that you use correct population and correct information to present your data. Now we're going to something really fun. We're going to incidence. So what are incidents? Incidence in the rate of new cases or events over specified period of population or period of time for the population at risk. So basically, we're taking all new cases of specific disease and dividing it by our population at risk, multiplied by some kind of time, follow-up time or disease time, like any time frame we want to calculate our incidence from. For example, you watch a group of 5,000 people in your town during the 5 years period, and 25 individuals were diagnosed with diabetes. What will be the annual incidence of diabetes in your town? So how you calculate your incidence? You have number of new cases divided by 5,000 people over the 5 period of time. Yeah. So you can calculate it that your incidence in this case will be 1 per 1,000 person years, people per year. So when you report incidence, you say person years. So it's risk population within specific period of time. So for example, I took here the table for the studies that measured estimated crude incidence. Crude, it means not adjusted incidence of diagnosis of diabetes among the adult population in the United States between 2018 and 19. Yes, so they're presenting here the 2 years. There was some difference in the notes of how they calculated it, but I'm going to look for the first column, population estimates, or estimates 2019, number is 1,000. So during this year, there were 1,395 people that develop the condition. And usually when you present incidence, you should present the confidence intervals to know what is the confidence intervals. And in addition here, they calculated this age-specific incidence. So they went and calculated what will be the population estimates of crude incidence of diabetes in each specific age group, and they presented it by age. Why I'm telling all this? Because it's very important later to understand what is risk population. For example, here I'm going to give a simple example of calculating the incidence in specific ways and adjusting the time frame. For example, a health worker finds that over the past 3 months, there has been 4 new diagnoses of lead poisoning in children in her community. She estimated there are around 60,000 children in her community that are at risk of lead poisoning. If she assumes a stable incidence of lead poisoning over the time, she can calculate annual person-year incidence of lead poisoning for the children at risk in her community. So there's different methods to calculate it for different times, but here I'm going to present the method that calculated people months. So it depends. I said you need to have your population at risk, and you also need defined in what time frame, what is your time units when you calculate the incident. So in this specific case, I would like to calculate it as people months. So this is basically my calculations for new cases divided by 60,000 people multiplied by 3 months. And it's given me the cases people months. And after that, I can present it nicely, because to present 0.0002, it doesn't make any sense. So I can convert it to 12 months per year, and I can report it as 0.24 cases per 100 people a year. So it's very important to calculate the incidence correctly, but it's also important to present your results that it's meaningful for people that are going to read it. Because if people say, oh, if people see like, or your readers see like 0.0002 cases per month, it's really hard to comprehend what was the incidence of risk poisoning in your population. But when you say, oh, there was 0.26 cases per 1,000 person years, it's much easier to understand in rational what were actually the incidents. And this is the one problem that I encountered when I did some of the requests of the analysis, when there was really big confusion between incidence and prevalence. It kind of looks the same because we measure cases during specific time for specific population, but incidence and prevalence are not the same. So what are the incidents? Incidence, based on definition I given before, it's a new cases, and prevalence, it's all cases. So for example, you have this cute picture in duck in the water. So the new water coming to the bucket, it's your incidence. New cases that come to previous cases that were already existed in your population, it will be the prevalence of specific time. And here, for example, water coming to the bucket and some water is dropping out, it's kind of death or recovery. So basically, those are the people that are out of your risk population because they're not at risk anymore in case you want to calculate incidence. So there are a lot of common errors that I personally seen when you calculating the incidence. And one of the most common errors for calculating the incidence is when we defining our population of risk incorrectly. We say, oh, we have this population, we're going to calculate the incidence over this population over a period of time. But it's actually what the most important thing in this calculation is to understand what is the population at risk. Yeah. So, for example, we know that each year approximately 61,380 individuals are diagnosed with uterine cancer. So when we say, okay, the population of this is population in United States, we will calculate the incidence, and our results will be 18.9 per 100,000 people years or person years. So we calculated the incidence, but actually in reality, only female are in risk of uterine cancer. So we can calculate it over the full population in the United States. We need to calculate it only on female population in the United States. So actually, when we recalculate it over the actual population at risk, the incidence rate of uterine cancer will be much, much higher because we use the correct population. And additional things that you need to know when you're talking about the incidence, that the incidence can change over the time. Yes, it's something not static, it's changing over the time. For example, if we calculate the incidence of chickenpox, historically, when there is not vaccine, we will have very, very high incidence of this disease in the population. But after the vaccine for chickenpox was introduced, the incidence rate decreased by 90%. So it's important to understand the risk population. This is it's very important to understand the time frame within which we're calculating the incidence. And we need to know that our incidence calculated in one country will be different, for example, from incidence calculated in another country, or incidence of the disease we calculated before might be different. For example, if you look on current COVID pandemic, yeah, the nature of the virus changed, the virus mutated, we have different mutation of the virus, and it's changed over the time. And if you look on incidence of people that were exposed to COVID and got COVID and people that died from COVID of the time, the incidence will be different in different point of the pandemic. So the next thing I wanted to talk, and it's my favorite, it's odds ratios. Because in the literature, in most of the papers you usually do logistic regression, and the results of logistic regression are usually reported as odds ratios. And I'm going to show you that you can calculate odds ratios from the modeling, from logistic regression. But actually, if you understand what odds ratios are, you can calculate manually without using any software. So what are odds ratios in probability theory? It's the ratio that compares the probability of event happening to the probability of event not happening. Yes, so if you look at it as in the lens of logistic regression, person can die or survive. So it will be probability of dying divided by probability of surviving. So this is our odds. So what odds ratios I actually measure? Odds ratios are measuring association between an exposure and an outcome. Represents the odds that an outcome will occur given particular exposure compared to odds that the outcome occurring what will be a odds of outcome occurring in the absence of this exposure. And it's most commonly used in case control studies. Basically, when you have cases in control 2 group, you can compare, but then it can be used in other study designs as well, but sometimes you need to have some kind of modification or additional assumptions to it. And this is if we're talking about the modeling. But if you calculate in the simple odds ratios, odds ratio is always a odds ratio. So I'm giving an example here of how to calculate odds ratio. If you don't have your computer and you don't know what model to use, you can calculate it very simple. Because as I said during my previous slide, in order to calculate the odds ratios, we need exposure and we need the outcome. So in here on the left, you see the table that says, oh, positive, they have outcome, positive, having outcome, and negative minus, it's not having outcome. And we have the plus minus for the exposure. And in the table, I put A is number of exposed cases, B is number of not exposed cases, C it's number of the unexposed cases, and D is number of unexposed cases. And those are even is the lead to our outcome to be 1 or not. So based on this one on the right, there is formula on how to calculate the odds ratio. So it will be A divided by C divided by B divided by D. So in the end, it will be AD divided by BC. So basically, we're taking like kind of crisscross or X in our table. So if you have exposed any exposure and any outcome, and you do basic frequency tables, calculate what are number of people in each of 4 categories, you can easily calculate what will be your odds ratio. So basically, in the end, we can say odds ratio is N of exposed cases multiplied by unexposed non-cases and divided by exposed non-cases and exposed cases. I think this is very confusing. So if you have your data and you created the simple table and I showed on the left, so you know that it's AD divided by BC, you will calculate your odds ratio without going to all those details. So here also I showed how to calculate confidence intervals for your odds ratio. So even if you're not running the model, you still can calculate the odds ratios. And I showed here the formula of how you can calculate it. And it's actually coming from logistic regression. This model is coming from logistic regression when regression is unadjusted. So basically, if you're running a logistic regression and having your outcome Y and your exposure X, you, by using this formula in using natural logarithm of odds ratio, you can calculate the odds ratio. And here you can see I use 196 because at 95% confidence interval. So if you remember, I talked for previous lecture about that. When we talking about normal distribution, we using that score. So 195, it will be 2.5% on each part of our normal distribution graph. So here I'm going to, I put the reference to the paper. So, and based on this paper, I'm going to explain how to calculate odds ratios in more details. Greenfield and colleagues looked at previously suicidal adolescents. The sample was 263, and they used logistic regression to analyze the association between baseline variables such as XX, presence of psychiatric disorder, previous hospitalization, and other with suicidal behavior in 6 months follow-up. So here I'm only going to show you kind of unadjusted estimates. Yeah, so basically in the study, 186 out of 263 adolescents previously judged as having experience of suicidal behavior, and they required immediate psychiatric consultation. And you had a group of 86 young people had been assessed as having depression as baseline, and out of them 77 young people with persistent suicidal behavior follow-up. And 45 had been assessed as having depression as baseline. So basically, I'm giving you here an example of how they divide their population, and I simplify this here as who having a suicidal behavior and who has the outcome. So you can see youth with persistent suicidal behavior assessed that had depression at baseline, we had them as 45. And those that didn't have suicidal behavior follow-up, assessed as having suicidal depression at baseline will be 86. And we can calculate two other categories based on the numbers presented in the example. And here in the example, I coded them from the same table from the slide before, is A, B, C, D. So we have response and outcome. So our A will be 45, B 86, C 32, and D 100. And based on this one, using the odds ratio formula, AB divided by BC, we can calculate the odds ratio for this specific example. And our conclusion from this calculation will be the odds of persistent suicidal behavior is 1.64 higher given baseline depression diagnosis compared to non-baseline depression. So we had a lot of numbers, we did a lot of calculation, we received our results, but actually we can explain what our results in a really simple way. Yes, as persistence of suicidal behavior is 1.64 higher given baseline depression compared with not given baseline depression. So a lot of numbers come up with two very, very simple conclusions. So now I show you another example, very simple. I did it in SAS. So it's how you can calculate odds ratios using logistic regression. So when we use logistic regression, we all know we will calculate, and this is unadjusted logistic regression. So basically we will have outcome and exposure. So we will get regression coefficient B1 as the coefficient in regression for our exposure. And coefficient B1 is estimated increase in the log odds of the outcome per unit increase in value of the exposure. Yes, so for each unit increase in our exposure, our coefficient will increase by log odds of this exposure. In other words, the exponential function of the regression coefficient E, like the standard 2.72, in the power of B1 is the odds ratio association with 1 unit increase in our exposure. And the example I get from the internet is adapted from Pethauser 97 paper. And they say, suppose that 7, and it's really old, now it's probably the difference between female and male will be different, and we will present results in different way. But suppose that 7 out of 10 males are admitted to engineering school, while only 3 out of 10 female are admitted. Yes, and we want to calculate the odds of admission by sex. So on the left side, we see the table. So admitted 1, not admitted 0. We have 1 and 0 for male and female, and we have the frequency of them being admitted to engineering school. When we use this table and run simple logistic regression in SAS and R or any other software, we will get some kind of output for our logistic regression. And this is the output I received. So intercept, it's our alpha, or A, like A, and our B coefficient for logistic regression will be here 1.6946. Yes, and based on this estimate of beta, using the formula E in power of beta, we can calculate the odds ratio. So here in logistic regression, you probably know, we usually use the term logit. So what is logit? Logit of P is actually natural algorithm for probability of success divided by probability of failure, and its logit of P will give our logistic regression formula in kind of linear way. So logistic regression, as I'm going to explain later, it's actually generalized linear model. What is generalized linear model? It's by transformation of our function in specific way, we will get the linear relationship. So by using the natural algorithm of probability of success divided by probability of failure, we will transform our logistic regression into the linear form. And based on this one, our odds ratios will be actually E in power of beta. So what we're going to do, we're going to use E in power of beta, and we will receive our odds ratio as 5.4. And if you can see if my SAS output, I can let SAS, for example, option to calculate odds ratios as well. And how I'm going to do it, I say, calculate the exponential of my estimates. So basically calculate my E in power of beta. But also because this was an adjusted model, I showed the example of how calculate and get the same odds ratio using our simple ABCD table. So odds of male get to the engineering school will be 7 divided by 3, and female 3 divided by 7. So if you use odds ratio formula, you'll get exactly the same odds ratio calculation as 5.4. So it's very basic, but I just wanted to show kind of how you can get odds ratios from logistic regression. And when you interpreting results of logistic regression, so you understand what are the odds ratios. Yes, that calculating for an adjusted model, they calculate your odds ratio in like simple way using pen and paper will give you exactly the same calculation as using logistic regression. Of course, if you're going to use additional factors for this model and additional factors for this regression, the odds ratios might be calculated a bit different. I'm early today. And the last one I'm going to talk, actually, I'm a huge fan of survival analysis. I love survival analysis. And I think in epidemiology, we use a lot of survival analysis and survival modeling. So I'm going to talk briefly of hazard ratio. So what is hazard ratio? Is a probability of event in treatment group relatively to control group probability of a unit of time. Yeah, so we're not measuring just risk in specific point, we measuring it as a risk over the time. And you're probably all familiar with Cox regression model. And for Cox regression model, we usually say Cox proportional hazard model. And what it means proportional here, we're going back to my first slide about what is proportion in mathematics. So proportional hazard model is meaning that you hazard over the time, each point of time is equal. So your ratio is not changing over the time. It's like a Cox considered proportional. So in order to run a simple Cox model, you need to ensure the basic assumption of Cox models that you hazard ratio over the time between your start point and end point is proportional or equal. So additionally, you can explain hazard ratio as an effect size measure for time to event data. So you have time to event data and you have some exposure or some treatment, and you want to measure the effect size over the time. So for as example, we can say use hazard ratio to estimate the treatment effect when you want to assess time to event. Hazard ratios can determine whatever a medical treatment reduces, for example, the duration of symptoms or prolonged survival in cancer patients. So to simplify, assuming that you tried new cancer medication, you followed up your patients for 2 years, and you wanted to see if your new medications actually contributed to prolonged survival from cancer. So here, like, it's look like that the hazard ratio in terms of representation, it's look like relative risk or odds ratios, because in all cases we are measuring the probability in 2 or more groups. Yeah, we have probability at risk or probability not at risk, or hazard ratio effect size over the time for hazard ratio. So conceptually, kind of, if you look on it, it looks like it's the same, but it's not, because the hazard ratio is reported only for survival analysis, and it's an equivalent part of survival analysis and how we present data for survival analysis. Here, like, I put the paper on the bottom from where I took the picture. So they measured hazard ratio, I think, of survival from cancer based on the smoking status. So for smoking status, they had quit less than a year ago, 1 to 5 years ago, quit greater than 5 years ago, and didn't smoke. So on the left, they presented the survival probability of the event as like Kaplan-Meier, and you can see like survival rates here. And also in the table, they presented the hazard ratios and of course confidence intervals, because in statistics we doesn't present anything without confidence intervals. As I said in my lecture about probability and what is p-value. So basically confident interval is something where we confident that we working with our hypothesis correctly, and this is why it's our confident interval. So 95% confident interval, because our p-value was 5. So p-value is the type 1 error, and our confident interval basically it's 1 minus 1 type error. So this is representation. So basically this is what I wanted to talk about, and I did some summary here. You can read it later maybe in more details if you decide to rewatch the video. So here I basically put in the table the application for relative risk, odds ratio, hazard ratio. So here we can see that the relative risk is commonly used in prospective studies, such as cohort study. Odds ratios are commonly reported in the medical literature, particularly to case control studies, and it's measuring of association between exposure and outcome. And as I just said, hazard ratio, it's kind of the same, but in survival analysis, and hazard ratio is commonly used in clinical trials, epidemiology, and other medical research to analyze the impact of the intervention on survival or time to event outcome. So basically, it's our risk over the time. So in next slide, I give summary of formula, like it's not necessarily formula, but how you're going to calculate. So relative risk will be risk of intervention divided by risk of control or placebo group. Odds ratio will be also odds in intervention group divided by odds in control or placebo group. And hazard ratio calculated using survival data, when hazard ratio is hazard rate in the intervention group divided by hazard rate in control group. And it's why, like for Cox model, you want it to be proportional, yeah? Because if your hazard ratio is changing over the time, So if you hazard in each group changing over the time, it will be really hard to calculate the ratio of both. But there are a lot of models that don't require this assumption, and you can do your analysis using survival data without assumption of proportionality, where your hazard ratio is changing over the time. Also, there is a way for you, for example, to use Cox extended model, that is a Cox model that uses for longitudinal studies. And for this type of model, it's important to check hazard proportionality for baseline characteristics, because they're not changing between your point baseline and your end of the study, but you don't need this assumption for your longitudinal outcomes that change over the time. And here's basically, I show what it means. So for all relative risk odds ratios and hazard ratio, the ratio can be 1. That basically is there is no difference between groups. So if you're going to run your model and you have something odd ratio is 1.1, it will suggest that there is no difference in odds between two groups. So here is relative risk can be either 1 or not 1. And if relative risk is not equal 1, it means that one group has higher risk than the other due to intervention. And odd ratio, hazard ratio, it can be the positive. It means your exposure group has high risk, and less than 0, that your exposure group for both calculation of odd ratio, hazard ratio will be, your exposure group will be in a lower risk. So it's consistent across all of those. And here I want to add again, and I talked about it multiple times, when you calculate odd ratios, hazard ratios, it's very important to look not only of your odd ratios more than 1 or less than 1, but also look on confident intervals, because if your odd ratio is like 2.5, but confident intervals is 0.75 to 7.5, you cannot be confident that you actually, the risk in the odds in your exposure group are higher than in your not exposed group, because your confident intervals are very wide and they overlap in 1. So this will be consistent for all 3 measures. That's it. Thank you. Let me know if you have questions. So what I wanted to say, so during this year, we have 3 lectures part of STAT series, and we also had 2 lectures as part of Lunch and Learn that are more like philosophical and broader about the data and probability. And those 3 lectures were like more related to statistics and what more targeted. So if you listen to this lecture or missed previous lectures, the first 2 already available online. You can listen to them. And if you have questions for any of the lectures or any question related of what we discussed during those 3 lectures, you can email me and meet with me and ask your question, and I can explain it to you in like more private way and only to your specific questions. So just send me an email. My email is available for our VHRI STAT services. Thank you. Bye.